Hello, I'm Rodney Schreiner from the Wisconsin Institute for Science Literacy and the McPherson Eye Research Institute at the University of Wisconsin-Madison. I think we've all heard the saying, seeing is believing, and that's easy to believe because our vision does a very good job of showing us what's around us and where things are located. But I have a question. Can you always believe what you see? Let's look at some pictures now to see if we can come up with an answer to that question. First, let's look at some arrows. Here are the two arrows pointing in the same direction. Now I'm going to place a drinking glass in front of the two arrows, so we look through the glass to see them. Now I'm going to pour some water into the drinking glass. I'm going to put in enough water so that we look at one of the arrows through the water. Look at that. The arrow that we see through the water seems to have changed direction. But did it really change direction? If I move the glass away, we see that it's still pointing in the same direction as the other arrow, but when we look through the water, it's reversed. Water has altered the path of light and made the arrow look like it's pointing in a different direction. On a hot summer day, the sun heats the pavement and the pavement heats the air above it, changing its density. And when light travels through this, it changes direction. And it can make it look as though the highway in front of us is wet, even though it isn't. Both of these, the arrow changing direction and the wet highway, are examples of what are called optical illusions. They are optical because they happen outside of our eyes. They happen in the world where light is changing direction. Now I'd like to show you another picture, this grid. On this grid, look directly at the center where a vertical white line crosses a horizontal white line. Keep your eyes focused on that spot. Now, while you are looking at that spot, notice that where other vertical lines cross other horizontal lines, you will see fuzzy gray spots. Now look at any of the other intersections of vertical and horizontal lines, and you will see there is no fuzzy gray spot at any of them. But no matter which one you look at, you will see fuzzy gray spots at other intersections. The fuzzy gray dots that we saw were not in the world around us. They were not produced by light changing direction. They were produced by something that's going on inside our eyes. Now let's look at another picture. This one involves color. Here we see the picture with a blue area on one side surrounding a gray box and a yellow area on the other side surrounding another gray box. The two gray boxes do not look exactly the same, but in fact they are. We can see that if we move away the white area in the center. The gray area is exactly the same all the way across. But when we separate it into two separate gray areas, they look different because they are surrounded by different colors. Sometimes it's good that we don't see exactly the color that is there. For example, when you're playing a game of chess or checkers and there are shadows on the checkerboard. Let's have a look at what happens then. Here we see a checkerboard with a red cylinder casting a shadow across the board. On this board, the dark square in the top row, the light square in the middle row, and the dark square on the bottom row are all exactly the same shade of gray. I can show this to you by covering up all of the picture except those three squares. And you see they are exactly alike. Now, just to be sure that it is those three that we were looking at through the mask, I'm going to put labels on those three that are the same. The one in the bottom, the one in the middle, and the one in the top. And now when I put the mask over them, you will see the labeled ones are the ones that are displayed. All are the same color. But no matter how hard you try, when you see the whole picture, they do not look alike. Visual illusions don't affect only the colors we see, but they can also affect the sizes. Let's have a look at this. Here are the two blue bars on top of the black lines. The blue bars do not look the same length, but in fact, they are exactly the same. You can see that when the two bars are near each other. But when they are further apart, the black lines affect the way they look, and they look different. So the surroundings of objects in an image can make us think that they are different sizes. For example, look at this picture of two signs in a hallway. It may not look like it, but both signs are exactly the same size. We can see that if we fade away the rest of the picture and leave only the signs. Then we see those two signs are exactly the same size. But the rest of the picture makes our visual system interpret those signs as being different. And in fact, if they were in those locations in that hallway, they would be different. They're not optical illusions, it's a visual illusion. This effect that sizes of objects depend on the surroundings in the picture was something that was developed in the Renaissance by artists who figured out a system by which to accurately represent objects and their sizes and locations in pictures. Now, perspective works from only one point. The observer needs to be in exactly that point in order for perspective to work. Perspective works this way also in photographs, because the photograph is taken from one particular spot, the spot where the lens and the camera is located. This is why the best seats in the movie theater are the ones in the middle, because when you are in a middle seat, you are located where the camera was located when it took that movie. So you're getting the best perspective view. Now let's look at a picture that was taken by a camera. This is a picture of the Leaning Tower of Pisa. Now what I'm going to do is show you two copies of exactly the same photograph. Notice that they do not seem to lean the same amount. One looks like it's leaning more than the other. Why does this happen? Because when you are looking at two pictures taken from the same spot, you cannot be simultaneously in the best spot to look at both of them. So one of them is going to look different than the other. So, now that I've shown you all these pictures, and we've examined them, what do you think? What is your answer to my question? Can we always believe what we see?